first law. Who can tell me what Kepler's first law talks about? Yeah, Vaughn.
All of the orbits are so they're not perfectly.
Yes. So all orbits are elliptical, which basically just means not perfect circles. Not perfect circles. Okay? So, let's talk about the Orbital Motion Lab and how we can confirm that. So, Orbital Motion Lab how does this show me that it's an elliptical orbit? How do we know from this that it's elliptical? Martin, what do you think? How does this show me that it's elliptical? Because it looks like a circle.
Is it the velocity vector like increases and decreases?
So we're going to get to that. That is because of it being elliptical, but it's of itself maybe not the best example, but it is because of that, yeah. Ashton?
Would it because it's staying 2 units away on the right and 2 units away on the left?
Yes. Look at the orbit here. 1, 2 grid spaces away on the right. 1, 2, and a tiny bit grid spaces away on the left. So if you look at the orbit, you'll notice that it is not centered perfectly on the sun. It's centered a little bit off to that. And so there is a little bit of a wider orbit than you would expect it to be. So that is proof that the Earth is an elliptical orbit. The Earth is closer to the sun sometimes and further from the sun other times. So for us, this would be in the winter, and this other side is the summer. Okay? So we're actually further away from the sun in the summer than we are in the winter. Good. Okay? Next. So, again, for number 2, how can we tell that Kepler's law? So, Earth is not always the same distance from the sun. Okay, Kepler's second law, law of equal areas. What's that one going to be? Gavin, what you got for that one? What's the law of equal areas?
The second one?
Yeah, the second law. So number 3 here.
Describes the speed of which any given planet will move orbiting the sun. So, like, the closer you are, the faster, and the farther you are, the slower.
Good. So let's make 2 things here. So the first one is the actual definition. So the actual definition is objects sweep out equal areas in equal times. So that's that. But the implication of that is that objects move faster when closer to the sun. So when the object is closer into the sun, the object moves faster. When the object is further from the sun, it's going to move slower. And you can see that in 2 different ways. So on here, you'll notice that the green arrow gets larger when we're closer to the sun. So at that point, so you can see at that time the arrow was pretty large. You go around to this other side. you'll notice the arrow doesn't go all the way to that second bar like it did before. So the arrow is a little bit smaller at that point. Not a lot, but it is a little bit slower. So that's what you would have for number 4. So, or for number 5. So for number 5, confirm this using the thing. The green arrow, the velocity arrow, is larger when the Earth is closer to the sun, and it's smaller when it's further out from the sun. So that's 5. So Earth's velocity is higher near the sun. So, number 4, so Roman, why do you think that summer is a little bit longer than what winter is?
Because Earth is moving slower.
Yes, Earth is moving slower when it's further out, and it's further out. It's further out in the winter, or sorry, further out in the summer. Do I have that backwards here? Yeah, winter is 89 days. It's closer in the winter. So in the winter, it's moving faster, so it travels that distance quicker, so the amount of days take less. In the summer, it's further out, and so the amount of days take longer. So summer is actually a little bit longer than what winter is. And spring and fall are the same length. I think spring and fall are both 91, I want to say. 91, 91 and a half, 92, something like that. I forget the exact number. But that's kind of how those work together. So again, for number 4, why is it Earth goes faster during the winter? Goes faster during the winter, so winter takes less time. And you can see that here. When we're closer to the sun, it's going to travel in, so I think this is broken up into months. You can see it's going to travel a further distance, so it's going faster. So if you're breaking it up into how much of the days does that get, that's kind of the idea. So each of these is the same area. So when we're further out, it's kind of a long and narrow triangle. Think of it as slicing up a pizza, but not evenly in the middle. And here is kind of a short, fat triangle. But they have the same area, and so that's why the speed changes. Okay? So that's the big thing to know about the second law, is what it is and why it makes the speed change. And then the last one was the one that was confusing people the most. Kepler's third law. So it's called the law of harmonies. There's 2 ways that you can describe it that go together. So the first thing is that the larger the radius, so the larger the orbit, the longer it takes. And when we say orbit, I'm talking about the radius of the orbit. And when I say longer, I'm talking about period. And so here's the second part that you should know, and that's the equation. Now, I'm not going to make you solve this out, but you should be able to explain it. And the equation is this. Period squared over radius cubed. It's not really an equation, it's a ratio. It's the ratio between period and radius. So if you increase the period, you're going to increase the radius as well. This is why Neptune takes so much longer to go around the Earth or around the Sun than Earth does. And that's why Mercury takes way less time to go around than the Earth does. And again, the reason is this idea about the larger the orbit, the longer it's going to take. But the ratio is this, period squared over radius cubed. And so what you should see between these numbers, the relationship you should find is one of two things. One, you should notice that as these numbers increase also. So that's the first thing. But the second thing is illustrated really well in the reading. This. Look at the ratio, period squared to radius cubed. Look at the ratio for all these different objects. Mercury, 0.98, Venus, 1.01, and then everything else, Earth, Mars, Jupiter, Saturn, everything else is all pretty much between 0.99 and 1.1. The only weird one really is Mercury. Basically, this idea of law of harmonies is there's a very predictable ratio between the different, between the object's radius and its period. Anyone want to guess why Mercury is the weird one? And it's not even that weird. Why would Mercury be the weird one? Ashton?
It's the closest.
Because it's the closest to the sun. Yeah. The sun messes with Mercury's orbit. And so because it messes with Mercury's orbit, it makes it not follow this quite as well as some of the other things do. The other thing to remember is these are ellipses, so the radius is an average radius. And so because it's an average, it's not the exact radius every time. That's why it's not a perfect ratio. Good. Okay. Any questions about anything there with the note stuff on Kepler's 3 laws? You're going to see stuff about Kepler's laws on the test, so make sure that you understand that. We've done a lot of things for this test, so there's a lot of things to keep in mind, so be careful. Questions on that one? All right. You can put those off to the side.